Howie, so maybe you can talk to that first.
So, my name's Howie D. Please, and I'm one of the builders of $50 hat. And when we say that it's a Pocketqube, it really is, because all the pieces inside, the entire satellite fits in my pocket because it's radiance in the satellite. So, there's boards and battery ready to go. It was designed to fit the one-piece standard, even though $50 has actually 1.5 space. So it has some extra space for rent, but you can find it. We have designated MO76 by MSAT since the three buildings are all cam radio operators. MO for Morehead. Although Michael Kirchhoff, being from suburban Detroit, says no, it's Motown 76. But okay. It's been on off about 6 months now. It is still working. And I also want to say, if you see something, say something, anything that catches your eye, have a question, stop me, and so we'll. And we never did this before. This started off, Michael and I, who had never met, attended a meeting like this in Lexington in 2011. And during that, we noticed there were a lot of people in the education community there. Everybody was interested in building satellites, and Bob put out a call for anybody interested in mentoring or participating in an advisory role, let them know. Michael and I both did. And we were calling in on webinars, weekly webinars. So I just adding our 2 cents in from our experience as amateur radio operators and also being employed in the electronics industry in various states. We got Stuart Robinson involved when somewhere along the way we decided that we were going to use this module built by Hope Electronics, the HAR-122, a small radio. He had a lot of experience interfacing with that. Projects he had posted up on the Pocketqube. So we thought about it for about 30 nanoseconds, says yeah, sure. And the next website. So we recruited him on the group. And well, one thing led to another, and eventually he says, well, you guys want to collaborate and build Pocketqube. So we thought about it for about 30 nanoseconds, says yeah, sure. And so that's how we got here. So we had no idea what we were doing. Absolutely not. None of us had been involved in space at all. The closest of the team is probably me. I've done system engineering and commercial satellite ground stations and networks, but that was it. None of us had ever thought about the other end of the plane and went outside. Michael is an embedded developer, and Stuart is an IT professional. So again, we had no idea what we were doing. We got a lot of good mentoring from Professor Twins. The most important thing he told us, the whole project, was you're better off having a working Sputnik than a failed Hubble. Build something that's going to work, don't get carried away. So every step of the way, we kept that in mind. So we said, okay, so what are we going to do? We wanted to keep it simple. The idea was we got involved in this because it was an educational process. And we said, well, the project that was started probably could have been completed in a year, but if everybody had gotten a jump start on the simple stuff. So we said, let's develop a simple platform that's easily reproduced. No special parts, nothing along lead times. Everything we bought was pretty much around the DigiKey catalog or from eBay. That's where the battery came from. We wanted to have a robust, simple communication system. We wanted to make sure that we didn't need a 30-meter dish to hear this thing, or a large satellite array. That was a little bit challenging since we only had 100 milliwatts of transmit power. So me and several others did the link budget several times, and we were convinced that we could do this with simple things. Everything was going to be open source when we were done. The whole idea of this was to build something, okay, here's how you do it, here's what we did, and for everybody to see. And that's what we did. So everything was done not only with the parts that are available to everybody, like I say, at DigiKey catalog, we took all the code, all the designs that we did, and we put it all up on a Dropbox for everybody to look at. All the tools we used, either was done with Eagle or KiCad. So the tools were open source. The pickaxe was all written in BASIC, using all the tools from the pickaxe website. So really, when we talk low cost, we're talking low cost. This is the block diagram. There's two PC boards and a battery, and that's everything. The power board consists of 4 PowerPoint trackers. We put 1 PowerPoint tracker for each side of the spacecraft. The thinking there was that the satellite's not stabilized other than the magnet side. So it will probably be spinning about the z-axis at minimum, probably wobbling, sun coming from all angles, and cells get exposed at different angles all the time. So we want to be able to capture as much power as possible. So the theory was that, okay, so if we have each cell at its maximum power point at any given time, then we should be able to maximize power. So that's what we did. So each side of the spacecraft is serviced by its own maximum power point control, and just sum the output controls together. There's no charging control per se on the battery. The output of the maximum power point trackers are set to about 4.1 volts, which is the maximum flow charge we want to have on a lithium-ion battery. And the lithium-ion battery that we use is a Kodak camera battery that we bought on eBay for about $6. And that we don't seem to overcharge it at all. We also have some current voltage monitors on there that feed back into the processor. And the processor board uses the pickaxe 40X2. Again, we'll program in BASIC. We have a Dallas semiconductor temperature chip on there, so that we get some idea of what the temperature is inside. And the radio's an RFM22 module, which is based on the Silicon Labs SI44, I think it is, single chip radio, designed for the ISM band. That gave us some good capabilities on the data side. The RFM22 has its own packet standard that's used for ISM purposes. So it had the packet controller, packet handler built in. It did CRC generation, checksum. It does some AFC control. So these were all nice things to have that we didn't have to worry about and didn't have to write code for. So we just had an interface to the radio. And we did a lot of testing on the ground. Stuart Robinson and his older brother probably walked 20 or 30 miles doing testing on this. Stuart is in the UK, so we had a lot of open land and feeds and stuff to try. Because one of the problems with working with ISM radios and other radios not designed for space is that there's not a lot of specs available, things like noise figure and so forth. Phase noise, and things that you might be interested in for a long, low, noisy link. So we had to sort of extrapolate that out. And we did that by doing tests on the ground. And Stuart went out and says, okay, today here's the link I did, and here's when it stopped working. So then we go back and try to calculate, okay, we knew what the transfer power was, we knew what the antennas were, we knew what we were receiving and when. Okay, now let's back out. So over that link, what do we think the noise figure might have been? We did several tests like that. And we sort of got some round numbers and kind of guesstimated. And we plugged that back into the link budget and said, okay, yeah, that would work. You know, that link budget, what data rates can we support? So we had to do a lot of extrapolating through experimentation. And it turns out our numbers must have been pretty close, because in the end, when we actually did get into space and we started receiving this and looked at, okay, we know how far away the satellite is, and we could just receive it when it was X kilometers away. Do the link budget, sure enough, using the numbers, that pretty much worked out right. So we did some good guessing. So anyway, so we came up with these different modes. We generated an FM Morse code beacon, and also some fast Morse telemetry at 120 words per minute. None of us copy 120 words per minute, but the computer does pretty good. We have the FSK packet, which is the native packet that RFM22 uses. Then we added an experiment in here, that was a packet with FEC. We decided that, maybe we could get a little bit better performance if we put some FEC on the data. So what we did, what Michael did is that he used some information from a data sheet made by Texas Instruments, and he adapted that code along with Stewart to into the pickaxe basic. So we take the payload of the telemetry and wrap it in some FEC and send it. And we also do conventional radio teletype, which is slow speed FSK using async data. Now, anybody who looks at this chip would say, but wait a minute, there is no FM on the chip. It's just MFSK, FSK. Stewart, in software, was able to simulate FM by just shifting the carrier based on the data. So data would come in, and he would figure out, okay, put the radio in CW, and then send it to this frequency, then move it to that frequency. And so we all done the software by basically shifting the transfer frequency of the radio at the rate that we need. For the RTTY, he also helped put a little tuning aid in there, so that the Doppler shift for at 400 megahertz from 750 km is pretty high. So in order to help manually tune this, before he starts sending the RTTY telemetry stream, he sends out a pip at each end of the shift. So he'll send a low tone, a high tone, a low tone, a high tone, and he'll send a few seconds of this, and milliseconds of this. And when you're tuning this in manually, now you can see those pips show up on your display. Well, you just center between these two pips. Now when the data starts coming, you're close enough to really manually track it. And this is the transmission sequence that we do. So we start off with a slow Morse message. Then we send out a ready packet in this FSK format. Then we listen. At that point, when we hear that ready packet from that, says, okay, that's our opportunity to transmit the command up to the satellite if we need to. Short wait time. Then we alternate between either a fast Morse or RTTY telemetry message. Then we send a data packet, and a data packet with FEC, and then we go into the sleep time. The sleep time is our power management cycle. This is how we manage power on a satellite. We monitor the battery voltage, and depending on what the battery voltage is at that moment, that determines how long we sleep. So this is sort of a dynamic way of doing this without having to go into any outside calculations. It's pretty straightforward. So far, it's worked fairly well. We've seen the battery stay pretty consistent. We haven't seen anything below 3.5 volts so far in 6 months. Also, on the slow Morse, we use the audio tone frequency that gives an indication of the battery voltage. So we started out at 500 hertz for 3.4 volts. And every 100 millivolts, we increase the tone frequency by another 100 hertz. So if nothing else, even if we're just sitting there listening to it on a small handheld, we can get an indication of what the battery voltage is. We did it for battery voltage. If you have a different experiment, you can do this, whatever data you want.
Sir? Yeah. Does the Doppler kind of screw it up?
It doesn't because it's FM.
Okay.
So if we did this, like say on the RTTY, where we're doing FSK, then yeah, it would. But since this is actually FM modulated, Doppler doesn't affect that. So this is the FEC experiment. What we did was we took the payload and we put some F-rate, F3 convolutional coupling on it, 4x4 nanometer. This is pretty basic. So we predicted we get about a 2 dB coding gain out of this. But again, we're working with a 8-bit microcontroller written in interpreted BASIC. So, and it doesn't do floating point calculations. So we had to kind of keep this simple. So it was a compromise on what can we do with the power that we had. And oh, by the way, this is all single threaded. So the clock is ticking while we're doing this. We're still evaluating this. We did more work on the front end because this was one of those kind of like last minute things. After we found out, well, we have a little more time, the launch got moved out a little bit. We said, hey, maybe we could squeeze this in. So we concentrated on getting it implemented, and it looked like it would probably be coded. And now we're just going back and saying, okay, now can we do this some more? And how much are we actually getting? So this is an ongoing process, and hopefully we'll get a few more runs out of satellite things some more time. But we have to get a lot of data back from users around the world who not only give us printouts of data, but doing IQ captures now that SDR radios are so common, and you get a $20 TV receiver and receive the satellite with it now, so that's pretty good. It acts as IQ capture. Then we have an SEU experiment that we're running. One of the things that we were concerned about, well, we were concerned about and is concerned throughout the do-it-yourself satellite community, as it were, is that what are the radiation effects on processors? We didn't have rad hardware parts available to us, so we were using everything, again, out of DigiKey, off the shelf, commercial rated, we were lucky maybe we find automotive rated. So we wanted to try to get some idea of, are we seeing any effects from radiation? So what we did was, in every program loop, we write into this 512 byte area of RAM, and then we read it back out, and compare it to the same pattern that we have stored in EEPROM. And if we see a difference, we log it, and do it again. And we do this every cycle continuously. So far in 6 months, we haven't logged a single SEU event based on this experiment. So it looks like the pickaxe and the picks in general are pretty resilient. Within the amateur radio community, there is a lot of rumbling and friction at times between the university community, people who are semi-commercial, and the amateurs themselves about spectrum and the use of space and the use of amateur radio, licensing, and so on. As hands, we wanted to make a token effort to say this, we're not putting up just another quote-unquote beat set. So we provided we couldn't have time or power, or it was outside the scope of the project to put a transponder. But we provided the ability for a user to send a message up to the satellite and get a response. So any ham radio operator can transmit a packet in the right format up to the satellite. The satellite will respond with an RSSR report, a signal report, how well we heard that packet. Right now, the only way to do that is to build up an RFM22 transceiver, amplify it, generate the packet, and send it up. All the directions on how to do that are on the website. So far, nobody's done it. So to entice people, the team has decided that we would award anybody who does a certificate of technical achievement signed by the developers. I guess nobody really cares, nobody's tried it yet. But also we're offering QSL cards. Anybody who even just hears the satellite, sends us some telemetry, we'll send a QSL card. Another hand, Mike Rupert, PK3WN in Germany, who is an avid telemetry collector. If the satellite goes up, it sends telemetry, he's on it, he's collecting telemetry of it, he sends a lot of telemetry. He also developed with a friend of his a sound card program for decoding the FSK packet that comes out of the satellite, which was pretty good, which means now you don't need the RFM22 and the packet handler. He's done all that work in software. So now he modulates the audio and spits out data, which was a big step forward. He hasn't released it to the public yet. Don't know if he will. We're trying to convince him to. It would be a great building block. And this is the QSL card that we're sending people. Anybody who sends in telemetry to us, we have the website, $50 sat.info. which is also the gateway to our Dropbox, which has all the files and data about the satellite. This is the picture of the satellite, is what the covers went on it. The top of what is the transceiver. You can see the SMA connector off to the left. That little blob above the board is the radio. That's the entire radio. Underneath is the master PowerPoint controller board. Under that, with a piece of Capital wire, is the battery. That whole thing fits inside here. So that's it. Again, go to $50sat.info, and you can get to the link to the Dropbox and all the files, schematics, PC board layouts, software, parts lists, everything you want to know about $50sat is there. The communications document that explains all the communications modes, how it's done, and all the details there. Any questions?
How much, did it really cost you $50?
Well, it actually costs about $50 per board. If you don't count the solar cells. Since,
What was your, I mean, just curious, what is your estimate of your not your labor cost, but obviously just your hardware cost, hardware and software?
Well, each board complete was $50,
Okay.
almost on the money. So that's $100 for the 2 boards. Battery, again, it's about $6 off of eBay. And everything else was open source. The development system, really there is no development system. It comes with the pickaxe processing. Go to their site and download it. The old tools to lay out the boards, run schematics, were all open source. We stayed under the size of the free version of Eagle. I used KiPad to do the PowerPoint tracker, which is free download. The circuit boards were all made in China, so that's part of the $50 for, the boards were made 10 at a time. They came out to less than $1 a piece. It cost more to ship them than to make them. All the boards were hand soldered. We didn't have, there was no outside assembly. We all built them ourselves. So yeah, I mean, if we bought the solar cells themselves, it would have been probably about $200 worth of solar cells.
Yeah, I mean, one of the things we always talk about, the key to innovation is to fail fast and cheap. And the reason I ask that is knowing that it's very small. I mean, what these kinds of platforms suddenly provide is the ability for lots of people to innovate, experiment at a very low price point, and you can afford to fail, which is the key to innovation.
Well, yeah, and one of the reasons why we broke this up the way we did is that even if you wanted to do a balloon launch and you didn't have access and you wanted to see how things work by altitude, you could scrap the PowerPoint tracker. There's the battery, and there's the radio. I mean, you could launch that in a balloon pretty easy and have all the capabilities. Since it's all basic, it's very easy to customize. This is definitely within the reach of a high school project, no question about it, and within the budget.
What kind of antenna system do you need on the ground side in order to close the link?
Reliably, a handheld Yagi will do like 6-element UHF Yagi with a low noise preamp on it is more than sufficient. Stuart's lucky. In the UK, apparently, the 432 band's a heck of a lot quieter than it is here. And he's been able to get a satellite with all sorts of interesting antennas. Most of the time, he just uses a quadrilateral helix, omnidirectional, a good low noise amplifier. He's also done it with a Moxon loop with very good success. He actually he rolled out a piece of paper and taped some wire down to make a loop and rolled it outside, no problem. Routinely, we have other people around using fiber-fiber helixes in the area from time to time, depending on the task. But yeah, usually 6-element Yagi is that typical. My group in Germany has a pair of 22-element Yagis, and when he sends his IQ captures, it's just amazing because it's like sitting there on the bench with us. And again, this is with 100 milliwatts.
So first of all, just incredible that it's lived this long and working so great. What's the status of the health and status right now?
Right now, what we're starting to see some roll off in the battery. One of the things that affects the battery the most, surprisingly, is cold. The lithium-ion batteries, when they get cold, the internal resistance goes up considerably. So what we're seeing is that we can almost tell the temperature more accurately by the battery voltage than we can from the temperature sensors. And so it'll drop 200 millivolts easily when it gets down below 0 C. So right now what we're seeing is in between charge cycles, we're seeing the battery drop to 3.5, 4 volt thereabout. That's about the lowest we've seen it to date. So based on what we've seen so far, if we did linear progression out, we could probably have another 6 or 7 months if it keeps going this rate. Because we turn off the transmitter and we get to 3.3 volts. And we might have gotten more out of that, but you know, in the lessons learned department, one of the things we did was that we were looking for how do we control charging, because again, commercial battery, we didn't want to charge it below 0 C. Everything we've read is that that's a bad thing to do. So the easy thing to do was to disable the Mental PowerPoint tracker outputs. So that's what we did. So we measured the temperature, it's below 0 C, turn off the tracker outputs, which means no false negative cells. What we didn't realize, and what we didn't know at the time, was how long it would take the satellite to come up to temperature. So we figured, wow, this thing's pretty small, it's going to hit the sun, it's going to get warm there pretty quick. And we find out that's not the case. And it could take half an orbit before it gets warm enough inside to turn the charge back on. So we're throwing away half an orbit's worth of sunlight. Yeah, that wasn't good. Well, in retrospect, what we should have done was just open the path to the charge into the battery and let the solar cells power the payload. And this way we would have taken some of the load off the battery and maybe things would have gone better. But, you know, next time.
In terms of orbit, do you just use the TLEs that are provided by Space Command?
Yeah. Yeah, that's more than accurate enough. Again, all the antennas we're using, even a 6L Yagi has at least 10 degrees of beam width. So that's more than accurate enough for any way to track with it. And those seem to be very, very, very accurate. And we can sit there and we use the tracker and it comes right up and the Doppler tracks pretty close.
So you're not seeing like a fall off in AOS, LOSs?
Not that we can detect. Okay. I mean, it's possible, but not that we can detect. Again, you know, when we're working at VHF and wide beam widths, it's kind of hard to just by track and determine what it is. Certainly the margin of error is outside what we can measure with the English. Okay. The stuff that's